All right, moving on to chapter 3, bioenergetics. Again, hopefully you're doing okay so far. Again, I'm going to try to get these out within the week that you have this information. But again, you also have the lecture notes as well as we're going through this. So again, I know that having a lecture, or at least someone teaching you, is a little bit different than you just reading it. But don't just use this. Use your textbooks. Read along with those. That should give you enough information that you need. Essentials from this chapter, so just understanding the basic terminology from this section. ATP, what's its role as energy, the basic energy systems and the ability of each of them. So we'll cover that. Effects of training on bioenergetics of the muscle. So what happens with training? We're going to introduce some of the substrates, so the substances or the ingredients, so to speak, of the energy systems, and then training programs with an understanding. So basically, when you start writing programs later on, having a sense of what energy system you're using is important, or what energy system you're trying to manipulate is also very important. Otherwise, it's a waste of a program, not a waste, but an ineffective and inefficient program. So some terminology, again, bioenergetics. So the flow of energy in a biological system. So essentially, what is that? It's the conversion of our food, so carbohydrates, proteins, and fats, into usable energy. So that's essentially why we eat. We need to provide ourselves with the ability to produce energy, and the macronutrients, so the nutrition, allows us to do that. When something is called catabolic, it is the breakdown of large molecules into smaller ones. So you have carbohydrates, think of a potato or pasta, and that getting broken down into its single glucose molecule. So a single, not single celled, but a simple molecule to be used for energy, or produced for energy. You can also think of things like muscle getting broken down, right? That is catabolic. Then when you hear anabolic, think building up. Now, not just anabolic steroids, but that's kind of where the term comes from, is that anabolic, we're building up. So amino acids building into certain proteins, right, would be an example. Maybe it's in your muscle, maybe it's somewhere else. But again, that idea of catabolic and anabolic. And what is metabolism? That is the total of all, both the catabolic and the anabolic reactions going on in the body, because they're constantly going on. Some things are being broken down, some things are being built up. And so your metabolism is the total of those things. Adenosine triphosphate, or ATP for short, that is the molecule used to drive anabolic reactions, right? So energy is being used. That's what's going to power muscle activity. If you remember back in chapter 1, where we talked about like the myosin heads attaching to the actin, right? So, and then it needing ATP to detach itself so that it could reattach and then pull and then detach with ATP, and so on and so forth. So that's just one example of the energy that it's used for. And we'll look at how it gets produced and how it's used in this section. So again, what is ATP? So adenosine, and then basically there's 3 phosphates. So that's what these little PIs are. And within each of those bonds, because again, they're bonded together, there's energy. Stored energy, potential energy. And then what happens is when it breaks off into ADP, you have that chain broken and you get released energy. So energy gets to be used. And so ATP is kind of this potential energy. It gets used for a bunch of processes, and then energy gets released from it. So that's kind of the idea behind it. Your energy systems, you might have heard them as different types, but we'll kind of be using these 3. So the phosphagen system, which is anaerobic, so doesn't use oxygen or require oxygen. Glycolysis is technically considered anaerobic, even though its byproducts will be used for the oxidative system. And then you have your oxidative, which is aerobic and is going to use oxygen along with some other products as well. So glycolysis is kind of this in-betweener. Phosphagen, think very anaerobic, very fast, very powerful. And then oxidative is aerobic, long-term energy usage. So again, phosphagen system, the primary source of its ATP is for short-term high-intensity exercises. So jumps, sprints, those types of things. But it will be active with all types of exercise. So you still will use your phosphagen system. It's going to definitely be used in these high-intense exercises. Again, what's those next two? So ATP becomes ADP, right? It gets broken down to produce that energy, and then it gets rebuilt ADP into ATP through what's called creatine kinase. Type 2 fibers. So again, if you go back to when we talked about muscle fiber type, so this is where everything kind of connects. So type 2 fibers have more phosphagen than type 1 fibers. So type 2 fibers, which were the high force, quick fatiguing, it would make sense that they like these high energy, short-term bursts of energy. So they have more phosphagen system type, or they use more of the phosphagen system than the oxidative system. Where type 1 fibers, which are, it takes longer to fatigue, they're going to have higher affinity for oxygen usage. That's going to be more of the other systems used. Glycolysis. So this is the breakdown of carbohydrates. So either glycogen stored in the muscle or glucose in the blood. So that's where you're going to get this energy used from. That's where the glyc kind of comes from. It's the primary source for high intensity exercises lasting up to about 2 minutes. Okay. So the phosphagen system is anywhere between 10 and 20 seconds, depending on who you talk to. And then anything beyond that, up to 2 minutes, is going to be glycolysis. So think 800-meter run, which would be 2 laps around a standard track, right? That's a lot at a very high intensity. That's like pushing the boundaries of that system. It occurs in the cytoplasm of cells, or the sarcoplasm of muscle cells is where this takes place. There's fast and slow glycolysis, which we'll look at. And again, sarcoplasm is where the muscle cell, that's the cytoplasm in the muscle cell. So that's where this is all going to take place. But again, so far, understand the difference between phosphagen, which is mainly going to use creatine, phosphate, and then glycolysis, which is going to mainly use carbohydrates. So not to get too far into nutrition, but you got to think about, if I'm going to use glycolysis, most people are going to recommend that you consume carbohydrates in your diet, because then those are going to be used for your energy for glycolysis, right? So that's why if you're going to do something with high intensity energy, a sprint, you're a football player, basketball player, where you have these high intensity bursts for up to 2 minutes, you're going to want those carbohydrates available to you. So here's just the difference between fast and slow. Anaerobic, so fast anaerobic glycolysis, the end product is what's called lactate, not lactic acid. We'll talk about that a little bit. It provides ATP at a faster rate than slow glycolysis. So again, you have this kind of differentiation between the two. Can be primarily used during resistance training. So think you trying to overcome a force for a while. 2 minutes of exercise is a lot with resistance training. And then just understanding what happens with it. So you have 2 glucose plus 2 phosphates, and 2 ADP is going to get you 2 lactate. You're going to actually get some energy on the other end of it, and some water. Again, you don't have to understand the chemistry of it too much, but just understanding what's going on. Your end products basically having 2 lactates. Then you have slow, which is aerobic glycolysis, but no O2 is really required. What happens is essentially your end product, pyruvate, goes to the oxidative system. So then basically it's not so intense that you are inefficient with your products. The pyruvate gets sent to the next energy system. It's used at typically lower intensities, such as aerobic. So again, instead of getting lactate, which is going to be used later, you're going to use pyruvate on the other side. You don't need to memorize this for me. If you're in any type of exercise phys class, you might need to, or physiology class, which is insane to me. But just understanding this is the process that things go through. Let's see if I can move this out of the way real quick, just so you can see the top. So you've got the very top, blood glucose. So again, this is your sugar or your muscle glycogen. So that's stored. And so basically from there, you're going to go through this chain reaction of your products. So you're either going to end up with pyruvate, which goes into what's called the Krebs cycle, which is the oxidative system, or part of the oxidative system, or you have your pyruvate, which is going to turn into lactate. Now, again, lactate isn't bad. Lactate just needs time in order to be converted back into energy. And when we build up too much lactate, that's where you start fatiguing, or that's a potential component of fatiguing. So just understand that. So that's kind of the 2 end pathways we were just talking about. So fast glycolysis is going to end up with more lactate. Slow glycolysis, you're going to continue to have pyruvate fed into the Krebs cycle as you go through. Let's get this back. So Glycolysis regulation, again, what stimulates it? It's stimulated by intense muscular activity. Okay, so right, that would make sense. Higher intensity activity, it's going to stimulate it. If there's phosphagen available, again, phosphates for that ADP to become ATP. Ammonia is one. A slight decrease in pH, so when things can become more acidic, your body wants to create a little bit more. And then AMP is just adenosine monophosphate, or a single phosphate instead of 3 or 2. What inhibits it? Very low pH. So if you get very acidic, think like ketoacidosis, that's going to shut down glycolysis, which would make sense. So you're not going to produce that energy. If you have enough ATP, glycolysis is going to shut down, or at least down regulate, which would be a good thing, right? If you're able to produce a lot of energy and you don't need to use all this energy later, now you can use it later. If you have enough creatine phosphate available, citrate is one, and then free fatty acids at rest. So the more free fatty acids you have in your system, think like ketones, or eventually becoming ketones, then you don't need that glycolysis, right? So the more you can, this is kind of into the nutrition health side, but if you can rely on fats as energy when you're at rest, that provides you more energy if you're going to consume carbs when you're in exercise, okay? Or more, you can save more there. If you're using glycolysis all the time, or you're always consuming sugars, that's where you can get, again, this is more the health side, like high insulin levels, insulin resistance, potentially diabetes and things like that. So shifting between those two energy sources, fats and sugars, can be very good for your health. Some of the enzymes, I know there was that long process or whatever, but just 3 to kind of be aware of: hexokinase, phosphorylase, and then phosphofructokinase. PFK, this is the rate limiting step. So if you don't have PFK available, then you're going to have issues with glycolysis regulation. What stimulates it, though, again, is the activation of the phosphagen energy system, so the fast energy system. Ammonia produced during high intensity exercise. Again, so if you produce ammonia and your body's going, wow, I need to not even filter it, but that means I'm using a higher intensity exercise, glycolysis is going to get upregulated so that it'll produce more energy. And then amino acid deamination. So when amino acids break down, you can use those as an energy source, and they'll kind of reinsert themselves into the cycle to be used as energy. Lactic acid and blood lactate. So again, the end product of fast glycolysis, lactate becomes lactic acid. We always have been, a lot of us have been taught that like the side aches we get or the fatigue we get is from lactic acid. That is not the case. What it really is the buildup of what's called hydrogen ions in your muscle tissue. So your blood tissue becomes more acidic. And that's what causes like the side ache or the pain, or you just have to stop exercising, is the buildup of that hydrogen. And so the better our body is at filtering out that hydrogen or being efficient with lactate, the more conditioned we are and the longer we can go at higher intensity exercises. Okay. But what is fatigue? Again, you're going to find all kinds of different things, but we'll just focus on inhibiting glycolytic reactions, right? So you can't produce that energy. Interferes with muscle action, so that binding or that bridging can't take place. And then again, decreased available energy and producing force. So you get jittery muscle reactions, you cramp, right? The body starts to shut down. It can be used, lactate can be used in gluconeogenesis, which is the formation of glucose. Again, as long as you don't hit that lactate threshold, which we'll talk about in a second, lactate is an energy source. It is an energy substrate. So it's not a bad thing. Okay, I want you to understand that. And can be transported to the liver and converted into glucose. So again, that's what will happen, right? It doesn't just burn your side and then disappear. It can get transported to the liver and then become glucose to then be used as energy. Okay, it's that buildup of lactate that our body needs to be able to filter through, where the liver needs to be able to convert it, where else is it going to go? So what is lactate threshold? It's the exercise intensity at which blood lactate begins an abrupt increase above its baseline. So you have this range, and then it kind of starts to go, and then it takes off, and you'll see that on the next slide. Usually begins anywhere between 50 to 80% of that maximal oxygen uptake. So again, that VO2. So more conditioned athletes can push that limit farther, where they can be at 80% of their max oxygen consumption, and then lactate gets intense. Some of us deconditioned, 50%. So not that much, and we're already hitting kind of that fatigue wall. Another thing is the onset of blood lactate. What they say is this is kind of when that concentration of blood lactate is near 4 millimole. and you'll kind of see again what that means in terms of lactate threshold and that increase. And again, the adaptations. So training at or near lactate threshold so that lactate accumulation occurs later at high intensity exercise. So this is that pushing the limit, but not superseding it. So let's just say that my lactate threshold was at 75% of my maximum O2 uptake. If I train at 70, 65, 70%, so I'm pushing it, but I'm not technically at my lactate threshold, but I'm producing and filtering out a lot of lactate, my body's going to adapt to become more efficient at whatever enzymes it needs, whatever transport it needs. It's going to, I'm telling my body to create more of that so that it'll filter that lactate and I'll be more effective at using it as energy. That's going to move my lactate threshold to the right on the graph. So it becomes closer to 75%, 76, 77, 80%. Now, again, that takes a while, but that's what's going to cause you. So then I can go at higher intensity exercise and still only be using oxygen as we go. Once you hit lactate threshold, what that means is that your body stops using the aerobic side and using the anaerobic side. And we've already learned that anaerobic doesn't last very long, right? You hit that wall really quick versus if you stay below that lactate threshold, then you can kind of keep going because your body just keeps using glycogen, right? Muscle glycogen, it keeps using glucose, or it can use that lactate. And so as long as you stay below that lactate threshold and that buildup of hydrogen ions doesn't occur with lactic acid, then you can kind of keep going. It's once we pass that when we hit that wall and we crash really quickly. So training that and finding that is the difficult part. But once you find it, sticking just below that, but challenging yourself can be really good for your training adaptations, if that's a goal that you have for yourself. So again, this is kind of what's happening. Let's start. So we'll kind of think on this side. So glucose and glycogen. Again, glycogen is just stored sugar. Glucose is just free. It's the single molecule. So it's going to go into the blood, right? Get transported to the muscles that needs it. It's going to go through that really crazy process that we looked at, glycolysis, that filtered into those two, either pyruvate or lactate. In this case, we have lactate being produced. That lactate is going to go into the blood, get transported to the liver, where it can get turned back from lactate into glucose, and you can continue through this cycle. The problem is when the blood lactate gets too high, we hit that that lactate threshold, right? And then we kick into anaerobic metabolism, and then that's where our performance starts to decrease. So as long as we can keep below that, we can keep this cycle going. And that's a training, and that's where you see athletes that are conditioned, right, versus deconditioned, or athletes surpassing what they're capable of doing. So here again is that line. So you have untrained subjects in the yellow, you have trained subject in the purple. LT is that lactate threshold, right? So once you hit that, it stays minimally low, and then you really see it start to skyrocket in an untrained individual, right? Whereas the trained individual can go at a higher intensity exercise, and then you're still going to get there at some point, but look at, now they have almost 25% more of a increased intensity they're able to train at without hitting that lactate threshold, right? And that blood lactate stays low, right? Where it doesn't get too intense and where we have to decrease our energy, our exercise intensity. So you can keep pushing kind of that limit as you go. So that's the training we're trying to adapt right there, is moving this dot farther to the right, as we do that. And then the oxidative system. So the primary source of ATP when we're at rest or for aerobic activities. Mitochondria is essential in this. That's where the Krebs cycle takes place. Uses mostly carbohydrates and fats. Depending at rest, again, that's where fat can be used as an energy source, especially if you're not snacking all the time. So if you kind of let your body, I use the term fasting or time restricted feeding, which includes sleep, right? Your body's going to use the fat stores as energy, or it can. So again, having flexibility, we call it metabolic flexibility, where it can shift between carbohydrates and fats is good. Some of us are way too dependent on carbs, and that might be increased health risk or things like that. But you also don't want to be, and so for those that are like ketogenic, for example, if you're on a keto diet, where they're like, they never have carbs, they're actually really restricted too, because they only use fats. And so sometimes, especially with athletes or individuals trying to be fit, you kind of want that flexibility where sometimes you have carbs. Now, which carbs is a different discussion. And then fats, using healthy fats, so to speak, is kind of an important aspect to use. And then again, the Krebs cycle is that what occurs in the mitochondria. That's where pyruvate comes in and gets used from glycolysis, produces these things that transport electrons to what's called the electron transport chain, where it gets you all of this really nice ATP, 36 to 38 versus the 1 or 2 from the other systems. So just thinking in relative, now that's a single glucose molecule becoming 36 to 38 ATP. Now, again, you have a lot of glucose, so that means you have a lot more energy. So just be reminded of that too. Again, don't get overwhelmed by the chemistry of it. This is the pyruvate, okay, that we just got from the glycolytic system. Okay, so it's the slow glycolytic system. But you also see if I can move myself. So you have fatty acids, right? So this is where fats can be used. So if you are keto or you're thinking about doing ketogenic diet, this is where you can get your energy from, where fatty acids can also fit into this system. They just come in as a different product called acetyl-CoA. And then you also have amino acids. Amino acids can be your energy source. And that's where people would drink like aminos during a workout, or even like your muscles might break down and provide some energy because they can kind of become these different parts of the system. So just know you have multiple sources to come from. It doesn't have to just come from glucose. Excuse me. But as you go through this, again, what you're getting out of it are these NADHs, okay, or your FADHs, and those are going to be used to transport electrons and produce all the energy that we're looking for. And again, this is your electron transport chain. So just think, here is your NADH and your FADH2. And that electron helps attach the ADP and become ATP. So this is where it's literally shooting out energy to be used. But you can only do this during the oxidative system or in the Krebs cycle, is kind of the idea behind it. So again, don't get too confused by it. If you're confused, Google the electron transport chain or YouTube it. There's plenty of videos on it. Khan Academy does some great things with that. So just kind of be aware of that. That is the why. So why do we have oxidative training, or why does it work? Why can we go long-term with oxidative? Because of all the ATP that we're able to produce compared to the phosphagen system or the glycolytic system. So here's your energy yields. So again, slow glycolysis, you're getting, and again, you're going to get different numbers depending on what textbook you listen to. This is straight from your textbook. So again, you have, so you have 4 or 6, right, from here, where the Krebs cycle, right, it's going to go through twice per glucose molecule. You're going to get somewhere up to 40. Some gets used, so they say about 36 to 38. That's in a perfect system. Again, we're not a perfect system. So again, just notice that. So 4 to 6 or 40, you're going to get, that many more times the amount, which is why you can go that much longer, right, energy-wise. So, and this is from fatty. So from a triglyceride molecule, or so from a fat, 1 molecule of glycerol can create 22. So 147 ATP per fatty acid, and you have 3 fatty acids on every triglyceride. So not to sound too crazy, but you have a glycerol molecule over here, and then you have 3 triglycerides, or 3 glycerides connected to it. So you have 3 fatty acids connected to a glycerol. And so the glycerol itself is going to give you 22. And then you have 147 ATP per each fatty acid. So you have 3 of those. So look at what the energy you can get from fat. And so I'm not going to go on my spiel too much right now about the benefits of fat, but look at the energy that you literally have on your body as body fat, right? Is all of this energy is stored energy that we're not always accessing. So for those that are trying to lose weight or use energy or use what we have, look at all the energy you actually have here, where we're always been told, like, eat a bunch of food, you need all this food. It's like, just for a second, remember how much energy you have stored up right now. And I'll kind of leave it at that at this point. Again, so energy production and capacity, this is kind of going back to those fiber types that also we talked about. So intensity, so higher intensity is power, or think power. That's going to be the phosphagen and glycolytic systems. Lower intensity is going to be your oxidative system, right? Because you can go longer at a lower intensity. Duration, shorter duration, again, usually more powerful, phosphagen and glycolytic. Long duration, oxidative, okay? Ranking these systems, so just understanding them. So again, phosphagen, fast glycolysis, slow glycolysis, and then oxidation system of carbohydrate, and then oxidation of fat and protein. So again, using different food sources is going to react differently. So how quickly is ATP made? Okay, it's made the fastest with phosphagen, right? The phosphagen system, but the capacity for it is the lowest, right? So it has the smallest capacity, but it's made the fastest, hence why you have a high level of intensity. Okay, working your way down, oxidation of fat, the rate isn't as fast, right? But your capacity of how much energy, which we just looked at, those 400 and some odd units of ATP, right, is ridiculously high. So I have this big energy pool. It just takes longer to make it, but I can keep making it, hence why the duration of my exercise can go longer. And so understanding the energy systems is important depending on who you're training or yourself or what you're trying to accomplish, right? If I'm trying to get more powerful, long, slow duration runs might not be the most beneficial thing for me. Likewise, if I'm training for a 5K and I've never done it before, doing high intensity box jumps might not be the most beneficial thing to me improving my 5K or my 10K speed, right? Or my running, my conditioning. So knowing what you're training or why you're training it is very important for the outcome that you're trying to get. Here's kind of the whole system. So again, you have your glycogen, right? Gets broken into glucose, goes through, this is a simplified version. You end up with your pyruvate. Pyruvate goes into acetyl-CoA, which goes into your oxidative system. Or you get your pyruvate becomes lactate. Lactate can then be converted back into acetyl-CoA or work its way back into the Krebs cycle. Again, you have triglycerides, so your fats, right? Those are also going to get moved into this cycle potentially, as are proteins. So all of your food sources can become energy at some point. Now, sometimes we want protein to not be used as energy, right? We want it for building up. Sometimes we want fats to be used as energy so we can lose weight, lose body fat percentage, I should say. And then sometimes we want that glucose for those high intensity exercises. So just understanding, again, where you're getting your fuel from and what type of fuel sources you need is going to become this dance and this artwork that this type of art that you create as a personal trainer, whether that's for yourself or for your clients. Again, just energy and event duration. We just talked about this. So very intense. So 0 to 6 seconds, you're going to use your phosphagen. You get up to 30 seconds, you're doing phosphagen and fast glycolysis. Up to that 2 minutes, you're getting glycolysis. And then you start working into your oxidative system with anything greater than 3 minutes. Okay, so that's 3 minutes on to hours, right? The 4-hour marathon, the 5-hour marathon, that's going to be your oxidative system. So again, just some practical applications with this. Understand your general timeframes. So what we just looked at, just understanding, have a good idea of what's going to be used depending on what situation you're given. Again, main idea, higher intensity here, short amount of time exercise can be performed, fastest producing amount of ATP. Fastest producing ATP, sorry, not the amount, right? Short amount of time, fastest amount of ATP produced, lower intensity, longer amount of time of exercise can be performed, but slower producing rate of ATP, not total, but producing rate. The client's training goal is probably the most important, right? If I'm a baseball player and I'm really trying to improve my speed from home to first base, that sprint, right, of 90 feet, that's going to require different training than training for a 10K. Right? Vice versa, my 10K, I may not need to sprint 90 feet or work on developing that system, right? That phosphagen powerful system. The first baseman probably doesn't, if they're only working on that speed, right? I shouldn't have them maybe running 2 miles and then hoping that translates, right? The body's going to adapt to the stresses that are put on it. So you need to put the appropriate stressors on the body to get the adaptation that we're looking for. And then these would be the practical outcomes of those things. And then recovery rates apply too, right? If you've done sprints, you realize how much you need to recover versus a long duration, you may not need as much recovery. And again, we'll talk about that when we get in the program design, but hopefully that makes sense for you guys. This was a turn-it-in activity. Again, for my in-person class, if you want to do it and just kind of work on it, by all means, but this is not due for you guys. So again, just think about the practical application. If you have any questions, let me know. Appreciate it. And I will see you guys later.